And it is our great pleasure to have Dan Steinberg, Professor Dan Steinberg from Oberlin College, as our colloquium speaker today. And then he did his undergraduate work in Williams College, right? And after that, he got his PhD at Cornell in 1982, working with Jim Cordes on pulsar scintillation and pulsar polarization. And after a 3-year postdoc at Princeton,
NRAO.
NRAO in Charlottesville, he had a chance to go to Princeton as an associate professor. And in 1990, he moved to Oberlin College as a professor. And I think some of you already know, but Dan told me that the Oberlin is close to Lake Erie.
Lake Erie, yeah.
One of the great America's Great Lakes. And he told me it is also a really peaceful and beautiful city for him and his wife to raise his 2 children. Yeah. And in 2019, he retired from the Oberlin College to spend more time for his research and his family, and also for selling their boat named Porous. So I think it is a really beautiful name for their boat. And his work, he has investigated on pulsar and interstellar scintillation, and he's also a very active member in a nanograph collaboration, which is using pulsars for detecting long wavelength gravitational waves. And I think he's going to talk about pulsar scintillation today. So please join me in welcoming Dan.
Well, thank you so much for that nice introduction, Sujin. And I really already feel very welcomed at the Institute. I've been here since about the 1st of February, and I really feel settled in and have even had a chance to get up to Alishan Mountain last weekend, which was a great pleasure. So I'm going to try to make this useful for non-experts. I only see one expert in the room, and and I can always talk to Dylan about anything that I didn't make clear. So I'm going to just try to introduce a technique to you that is actually quite active in this building. Wei-Li Penn is one of the people who really originated the sort of modern version of what I'm going to be talking about. And so, so let me go ahead and start by emphasizing that in astronomy, we always have trouble with that 3rd dimension, right? We see 2 nice dimensions on the sky, but figuring out how far away something is always difficult. And before I go any further, please feel free to stop me or interrupt me if I say something that's not clear or you want some elaboration as I'm going along. So in astronomy we have some wonderful relationships. We can, Henrietta Leavitt around 1890 developed a method to find the absolute luminosity of Cepheid variables, and that then revolutionized one way of doing the distance scale. And we know in extragalactic astronomy, the Hubble relation allows us to take an easily measured redshift and convert that into a distance or a look-back time or anything like that. And now in the era of Gaia, where Gaia is just doing this extraordinary parallax measurements, we have distances and proper motions to a very large number of stars, out to about a kiloparsec, if I'm not mistaken. In the interstellar medium, which is the part of astronomy that I'm primarily interested in, distance measurements are also tricky. And one of the reasons why this is true is that many of the measures that are easily measurable are integrated measures, and one of these is the so-called dispersion measure to pulsars, which is an integration of the column density. It's the column density of free electrons along the line of sight. It's the, as you can see, it's the integral of the electron density along the line of sight. And easy enough to measure, but hard then to know exactly what portion of that line of sight we're really focusing in on. This is just a reminder of what dispersion looks like observationally. This is actually a fast radio burst, and so about just a few milliseconds wide, and it sweeps from high frequency. It arrives earlier, and then because of interactions with the electrons in the interstellar medium, it then arrives later in a 1 over frequency squared kind of sweep, very strictly adhering to that 1 over frequency squared. And so just by measuring the the slope of that line, or the actual track of this line, it's easy to arrive at this dispersion measure. But again, with the problem that it's an integrated measure. So you'll notice before I leave this, there's one other effect here, and you can see that the darkness of this trace varies along this path. And that's because there's another effect going on here. And not only is the interstellar medium dispersive, but it's also inhomogeneous. It's clumpy. And because of that clumpiness, there is scattering in the interstellar medium. And that scattering has some very interesting and powerful consequences. So I want to go back to 1970, just a year or so after the discovery of pulsars. And my colleague and friend Barney Rickett was one of the first people to be studying some of the details of the newly discovered pulsars. He was working at Jodrell Bank, and this is really the first paper that shows the kind of, this is time, I'm sorry, this is, yes, this is time running upward like this, and this is 2.5 megahertz of radio frequency centered at 400 megahertz. And what you can see is that there seem to be islands of power here, regions where in the frequency time plane, in the dynamic spectrum plane, where the pulsar is quite strong. And then there are places where it's quite weak. And so this was a first puzzle that people had to deal with pulsars. And perhaps you know this phrase that when we take friends out to show them the night sky, and everybody's interested in, well, where are the planets? Can you show me a planet? And one of the easy things to notice about planets is that planets do not twinkle in the Earth's atmosphere because of atmospheric turbulence, but stars do. Well, on a much, much smaller angular scale, pulsars twinkle in the interstellar medium, but quasars, which are much, much more distant objects, actually don't twinkle or scintillate in the interstellar medium. And the reason is because they're just not as, the angular size of quasars is just not as small as that of pulsars. So with that as a setting, I want to make this a human story, because actually at my age, one of the great pleasures of thinking about my own career and thinking about doing science is to think about the friendships I've made along the way And honestly, as the enormous pleasure that I've taken from all the intellectual interactions through the years, the other thing that's great about doing astronomy and doing international astronomy is the kind of friends you make along the way. And so this is Barney Rickett and his wife and my wife Lynn, and we got a chance to visit with Barney and his wife Holly in near their home in San Diego about a year ago. And in fact, just this morning, I wrote Barney, when I put this picture in the slide set, I wrote Barney and said, there's going to be a scintillation meeting in Taiwan in November. Let's go together. And so let's get these two couples back together and let's go to the meeting together. So we'll see if that happens. I hope it does. Colleagues and I, Barney and I in particular, have recently done a study of 22 pulsars. This is one of them by name. And in that study, we observed most of them at 3 separate observing bands. And so each one of these is a dynamic spectrum. We have radio frequency vertically. We have about an hour's worth of time horizontally, I guess a little bit more here. And what you can see is that these intensity maxima, these black spots here, have a different frequency scale and a different time scale in the 3 observing bands. That's well understood. It follows naturally from some of the details of the theory of scintillation. We could go into that some more if you have a particular interest in that. But what I want to move toward is a more detailed kind of analysis of these dynamic spectra. And if I wind the clock backwards about 25 years, the primary method, the primary analysis tool that people use to analyze these dynamic spectra was the 2-dimensional autocorrelation function. And a 2-dimensional autocorrelation function, as you know, is excellent at characterizing scale sizes in an image like this. And so, for example, if we're looking at something like this and we do a 2-dimensional autocorrelation function, we're going to pick out a frequency scale and a time scale for these maxima, and that is quite useful. You also know, and I'm getting a little bit ahead of the story, but I might as well say it now, you also know that the autocorrelation function is the Fourier transform of the power spectrum. Those are, they are a Fourier transform pair. And so because they're a Fourier transform pair, they have exactly the same information because the Fourier transform is just taking us into a different domain, but with the same information. But it turns out that the information is packaged differently, and in the particular application that I'm about to show you, it turns out that the 2-dimensional power spectrum has been much more informative about what is going on in the scintillation pattern than just the 2D autocorrelation function. Let me show you more about this. So first of all, here's the kind of picture I'm talking about. We have a pulsar over here. We have some kind of scattering screen, and then we have, in this particular picture, we have straight line propagation until we get to the screen. The screen has density fluctuations in it. The density fluctuations deflect the individual rays, and they then arrive at the telescope, having different path lengths. And a crucial fact here is that because the pulsar is so small, i.e. pulsars twinkle in the interstellar medium, the radiation here is coherent along each one of the paths. In other words, the electromagnetic phase of the wave has been retained. And so when we recombine all the signals here, or when they recombine themselves, there is interference between those, and we get either an interference maximum or an interference minimum or something in between, depending on exactly where we're located on the scattering screen. So in other words, spatially there is a random interference pattern at the observer. But then because the medium is dispersive, that the actual combining of all of those phasors at the location, at any particular location, is also a frequency dependent or wavelength dependent quantity. And so that really explains in a qualitative sense why the dynamic spectra have these interference maxima in frequency and time. So I want to move the story forward to 1997, and actually it was January of 1996, and I went to a pulsar meeting in Sydney, Australia, and Barney Rickett was there, and he showed, he had a poster presentation that ultimately ended up in this paper. But when I saw this poster, it just completely floored me, because I had been worrying about some subtle issues in pulsar scintillation at that point for about 6 years or so, 6 or 8 years, the time I had been in Oberlin and had been working on things, and I had been noticing some patterns in the data that didn't seem to have a good explanation. And then he showed this this plot. Now, unfortunately, the combination of the screenshot that I did and then the projection, I mean, this projection is quite high quality, but nevertheless, you're missing the, you missed the crucial feature here. What you can see in the original journal article is that there is actually a striped pattern that runs along parallel to these two lines and can be seen going across this this dark scintillation maximum. And if we look at the two-dimensional power spectrum of this, which they showed in their paper, then in addition to this central maximum, there was an island of power that they showed over here, or that came out, that is exactly that two-dimensional sinusoid that shows up in the dynamic spectrum. And so this is really remarkable. This is not the only time that this had been seen or reported in the pulsar literature, but it had a very, very big impact on me, and it was very exciting, and it was very clearly presented, and this is the kind of scenario that they're imagining. Pulsar observer, and this is a figure from their paper, and they're imagining two different ray paths, one where something like 99% of the flux travels along here, 1% of the flux travels along here, they recombine, and because of the time delay, and because there is a transverse velocity in the problem, you end up with this patch of power over here. So very exciting stuff, and let me just show you the kind of observations along these lines that we're now able to do, and then I will have a slight digression where I show you a few of the details of why this works the way it does, some of the physics behind it. But let's look at some pretty pictures first. So, this slide, which I think I've already shown you, is these three dynamic spectra for this pulsar at these three different observing bands. And then if we go ahead and look at the two-dimensional power spectra of each of those, and instead of saying two-dimensional power spectra every time, I'll use this shorthand that is not very creative, but it's but we call these secondary spectra. It's the spectra of the spectra, and so when I show you these, let me note that we've moved from a linear power grayscale to a logarithmic power grayscale. So we're looking at actually, and this is logarithmic power in decibels, and so we're typically looking at about 40 decibels, or about a dynamic range of about 10 to the fourth. A lot of, most of the data that I'm showing you here are taken with the Green Bank telescope, although we also reported some observations from Arecibo for a few weaker pulsars. And so this whole pattern will become clearer in a moment, but at the lowest frequency, we see most of the power here near the origin. And then middle frequency, this central power near the origin. But as we get to the higher frequency, we start to see something that looks arc-like. Let's look at a few more of these to see if this is some kind of general feature, or if this is something, just a kind of a random sort of thing. Well, of course, because I said it that way, it's not a random thing. This is this kind of parabolic arc that becomes more pronounced as we go to high frequency, is actually seen in most of the 22 pulsars in the sample that we investigated. And we tried to choose these pulsars basically just based on their dispersion measure and their flux density. We tried to make this a representative sample. And so you can see that we're getting some very nice parabolic kind of structures that get stronger as we get to the higher frequency. The fact that we're looking at an upside down version of that too, you've probably figured out by now, is just the fact that because we went in with a real valued function, the dynamic spectrum, then the power spectrum is reflection symmetric about the origin. Okay, and I think I probably have another one because I can't resist these because they're so beautiful. And so you can see that the fidelity of these is very high, and we get this pattern of, as we move to higher frequency, where the scatter broadened image on the sky becomes smaller, or the set of rays traveling through the interstellar medium is more confined. We get this very pronounced kind of parabola. Okay. I want to highlight two other people who have been very important in this story. Wei-Li Pen is well known to people around here, and this is a picture taken from this trip. And as you know, Wei-Li is a very energetic person who is full of all kinds of ideas. And around 2011, according to my calendar, he and I started to have some phone conversations because I had published some papers about these scintillation arcs. In fact, in 2001, I published a paper along with some colleagues where we basically identified this as an interesting phenomenon and one that we saw in 4 different pulsars. And in my slow kind of way, I continued to follow this out, and I published a few more papers over the next 10 years or so. And there a few other people were interested in this, and there, you know, in our small pulsar community, there were a few people that were taking note of this. But around 2011, Wei Li got interested in it. And Wei Li, over the next few years, Wei Li was talking to his colleague Martin van Kerkwijk, and actually in 2015, Wei Li came down and visited me at Oberlin, and he was putting together some ideas that that hadn't occurred to me. And in particular, he was using his strong background in interferometry and bringing that in along with the scintillation behavior of the interstellar medium, because he realized that there was a lot more information here than we were than we were exploiting, and so I really think that Wei Li and Martin van Kerkwijk are the people who then are responsible for launching a small cottage industry of activity in this field called scintillometry. And over the last 6 years or so, we've had an annual meeting where people have come in, and first the meetings were small, but I think we had 60 or 70 people in Toronto this past year, as well as some quite a few remote participants, and it's really taking off as a field. And I encourage those of you who are just getting started in some of your own work to take a look at this, because there are a lot of powerful techniques that are still being developed, and you can be part of this. Now, I'm not going to I have 2 or 3 slides to explain this in detail, but I'm not going to dwell on them for very long, because I'm just going to try to give you the basic idea. Don't worry about the details of the equations unless you're particularly interested, in which case we can look at them together. But I'm simply taking a situation where we have an incident plane wave and it's hitting 2 slits. Okay, so it's double slit interference. This is a coherent wave. It comes in, hits the 2 slits, and there is a bending here, and one ray travels to the telescope here, one ray travels like so. It's easy enough to calculate the extra path length of this ray in terms of this angle at the observer, theta. We divide that by c to get the extra time delay. We then invoke the fact that there is an uncertainty relationship between a time delay and a frequency modulation in a spectrum. And so that then says that if we have a time delay of, for example, 1 microsecond from one path compared to the other path, then order of magnitude, there is going to be structure in the spectrum on about a 1 megahertz kind of scale. There is a factor of 2 pi in there, but order of magnitude, it's just the inverse of the time delay. And that means then that a time delay of 1 microsecond is going to be putting this 1 megahertz kind of structure into the spectrum. And then when we do a Fourier analysis, what we're talking about is we're talking about a fluctuation frequency. We need to know how many cycles per megahertz we have, and so it's the inverse of the actual modulation period, and so the actual number of cycles per megahertz turns out to be proportional to theta squared. That's the real take-home message here, is that that one axis in the secondary spectrum is proportional to theta squared. Let's do something similar. Again, the same setup. We've got a plane wave coming in. We've got a double slit here. The other thing that does, of course, is that sets up a sinusoidal interference pattern on a distant screen. Well, and so here's the sinusoidal interference pattern on the distant screen. If we happen to be moving through that at some velocity v, or if it happens to be sweeping past us at some velocity v, then we will end up with periodicity in time now, or then in the Fourier conjugate time axis, there will be a fluctuation frequency that is now proportional to just theta. So we had one axis proportional to theta squared, one axis proportional to theta, and this is what I'm saying here. If we then look at the relationship between the axis that is conjugate to radio frequency and the axis that's conjugate to time, we can see that there should very generically and very robustly be a parabolic relationship between the two, and that parabolic relationship between the two is set by some curvature parameter that is frequency dependent and also velocity dependent. And so in general then, we're going to have F nu. Notice that the axis here, we're going to have F nu proportional to Ft squared. That's the parabola. Also notice that we could be expressing this axis in cycles per megahertz, but if you think about a cycle per megahertz, that is also a time, right? And so again, this gets us back to the nature of that extra time delay. And so this is 6 microseconds of delay. And likewise, but sort of a little less obvious, on the time axis, it turns out that what we're also looking at, or another way of thinking about this, is we're looking at a differential Doppler shift between the reference beam and any other beam that is coming in, or any other ray. Okay, so I've thrown a lot of details at you. There's, you can see there's quite a bit to this. I'm going to do one last little thing here before going in a slightly different direction. And that is, I want to emphasize that to really get that strict parabolic kind of behavior, we need to have a very tight relationship between time delay between time delay and the differential Doppler shift, or the fluctuation in time. And if the scattering is occurring in a screen that's quite localized along the line of sight, we get an exact one-to-one kind of relationship between those two quantities. On the other hand, if the medium is distributed from me to you, and the rays are random walking their way from me to you, that tight relationship between time delay and the effective Doppler shift is broken. And so we don't expect to get that kind of sharp parabolic signature. So whenever we see a sharp parabolic signature, or a sharp parabola in the secondary spectrum, it's telling us that scattering has been localized to a particular screen, to a particular location along the line of sight. Now, there was one important detail that I did not mention earlier, and that is that the time delay only depends on the actual extra path that the ray follows along the line of, from me to Jeff. But the Doppler shift depends on how I'm moving along an axis, and in particular, if the image of the pulsar on the sky happens to be quite one-dimensional, which many of them turn out to be, then the angle between that one-dimensional axis on the sky and the effective velocity vector enters into this picture. And so, so that needs to be accounted for, and in order to, if we don't have information about that, there's actually a degeneracy between, or what I should say is that just measuring the curvature of the parabolic arc is not sufficient to locate the scattering screen along the line of sight. We need some additional information in order to be able to extract that directly. Unfortunately, clever people out there have been doing this, and I'm going to show you some early data from my own work, but that's not to imply that I'm a clever person, because the people who have taken this and followed on have done much more, much deeper analyses than I did. But anyway, the velocity is a combination. It's a weighted combination of the pulsar velocity, the observer velocity, and the screen velocity. And this is just a fractional distance from the pulsar to the observer. And this is the curvature of that parabola. And you'll notice that this effective velocity then appears squared down in the denominator. And so, again, I'll just show you one early version of this. I made this plot in 2003, and so we had data on a bright pulsar from Arecibo. This is 365 days in the year, and we were able to fit the curvature data that we had. This is due to the Earth's orbital motion around the sun. That was causing a modulation of the curvature. And this really amazed me when we did this, when students and I did this first plot, namely this 0.37 is not quite in line with, with the best fit to the data. 0.38 is a better fit to the data. And what I'm saying is that you can see that we're able to bound the location of that screen to within just a few percent of the total line of sight distance. Or to say it another way, it appears that that material that's giving rise to the scattering is localized into that very small region along the line of sight. And unfortunately, this beautiful green dot has disappeared, and I wonder if, but no matter. Okay, I'm going to now switch to some totally remarkable work that Daniel Reardon and his colleagues have done recently using the fabulous new instrument in the Southern Hemisphere, namely the Meerkat Array in South Africa. And he reported on this, unfortunately, he reported on this at the scintillometry meeting in Toronto in late August, and he did so remotely. And he's reporting on a pulsar that is one of the nearest pulsars to us. It has a dispersion measure of 2.6 parsecs per cubic centimeter. It's known to be about 160 parsecs away. And it also is known to have a bow shock as the pulsar moves through the interstellar medium. Now, I didn't quite get a chance to look back to Andy Fruchter's paper from 1995. This pulsar is in orbit around a white dwarf. Does anybody, Dylan, do you happen to know, is that an image of the white dwarf? You don't know? Okay. So we'll have to, that would be interesting to find out, because it'd just be interesting to know where the pulsar is. And I think it's quite plausible that that actually is the white dwarf, and of course then the neutron star is in orbit around that. Would anyone happen to have a little laser pointer? Which one? It just makes it easy to point at things, but this maybe, is this? You know, it's, I think we're fine. Yeah, thanks for trying anyway. So, to stay with this story, so Reardon did a kind of secondary spectrum analysis of this pulsar with Meerkat, and the results he got are just astonishing. This is just incredible. So this pulsar is 160 parsecs away, and he has identified 20 different discrete scattering screens along that line of sight. And so on another slide, he estimates that that means there's a scattering screen about every 5 parsecs along the line of sight. Now, we do not know what is causing the scattering. We do not know what these entities are. They're not stars, and they're not known supernova remnants or anything like that, which of course would be much less frequent than that kind of separation in space. And we do have, people have proposed some ideas, but honestly, this work has only been out there for about 6 months, and this is not the same kind of field as, say, fast radio bursts, where someone, produces a plot like this, and 2 days later there are, there are five papers written about it and posted to the archive. Things move more slowly. But anyway, fabulous work. It's going to be very exciting to see how this goes. And what I would point to here is this is a super bright pulsar and a gigantic collecting area and beautiful analysis. And so that combination, I think, is showing us what's truly out there. And I think the kind of lower signal to noise sort of observations that we've been able to do more generically has tended to pick out 1 or 2 or 3 of these scattering screens that are the most prominent ones. But and you can see, right? These are more, the ones in here are more prominent than the ones in here. But yet with, oh, thank you so much. Oh, that is great. Fantastic. Okay. All right. And so, you can see then that there's a selection effect here, but then with superior signal to noise and very careful analysis, there's a lot of information that can be extracted. And this is, again, I'm pulling shamelessly from the from Daniel's PDF from the conference, and 20 arcs one per every 5 parsecs. We're missing some due to signal to noise, and he's able to clearly see the that bow shock as the pulsar rams through the interstellar medium. That bow shock is one of the screens that he's able to identify, and he's able to solve the 3-dimensional velocity of the pulsar and of the shock and the shock geometry as well. So extraordinary stuff. It turns out I'm actually wrapping up now, so this is good, and because we'll have time for questions. So I just want to leave you with this thought, and so this is a picture of the very earliest redshift kind of diagram that was published. I don't see anybody old enough in the audience to really have been around and active when this was published in '86. But what we're looking at is this is redshift outward out to I should have said, we're now talking about extragalactic astronomy. We're looking at galaxies with measured redshifts. This is out to, the Earth is here, we're out to a redshift of 0.03. This is one of these famous slices, thin slices of the sky. And now this is a range of right ascension here. And this was the first indication that the galaxy distribution was not just a completely random distribution, but actually had some sort of cellular structure to it. And so that was 1986. And 17 years later, this was the state of the art, and better things exist now, but this is in 2003, and remember that redshift, the last slide was just out to 0.03, and I think the so-called frogman figure that is seen there, that is really the coma cluster, is right here, but you can see this sort of cellular structure in the redshift distribution of galaxies, or the 3-dimensional picture of visible light in the universe. And so there's been a huge paradigm shift in astronomy over the last 20 to 30 years, with the recognition that in fact the 3-dimensional distribution of galaxies in the universe is quite foamy or like a network, and of course the details of that are still being worked out, and the physics, the astrophysics behind that is still being worked out, but it's clearly a huge story. And in our own much more modest way, I'm suggesting that we're starting to understand the ionized interstellar medium differently, and we're starting to recognize that this picture that we had of basically a space-filling plasma with Kolmogorov turbulence throughout that then causes dispersion and scattering of radio waves is far from accurate, and that a much more patchy, maybe foam-like kind of structure is implied. And these conclusions from my own talk are similar to what Daniel Reardon was concluding, but I was working with a data set that had a much coarser view of this cellular structure, whereas because of the enormous dynamic range in his data set, he was able to see much finer scale structures. So in fact, as I was thinking about this, you know, before the scintillometry meeting and so on, I was thinking about structures like the local bubble that the, you know, out at about 75 to 125 parsecs around the sun. I was thinking of those as the prototypical kind of scattering structures. But that can't be right, because what Reardon is showing is that, in fact, these things are much more, they're much more frequent out there than that kind of separation. But we also have information in our data set, and I'm sure it's true in his data set, that in the scattering screens themselves, there is very substantial structure on an AU kind of size scale. And I haven't focused on the evidence for that in my talk today, but there is good evidence there for that. So I'll go ahead and leave that as my last slide, and I'll be happy to take any questions.
Thank you so much for that, for the very interesting and informative talk. Is there any questions you have?
Thank you. Wonderful. So one question is, if you can see multiple arcs, does that mean it's mainly a single scattering in each of the screens instead of like random walk?
Yes. Let me see if I'm catching an important part of your question. Are you also wondering whether there's any evidence for interaction? So if we're sending radiation through a set of screens, you know, the simplest kind of behavior would be one scattering happening in each screen. But then, of course, as the scattering strength, but let me, before I continue, are you also interested in, well, what about multiple scatterings?
Right. I was wondering if the multiple scattering happen, then you probably won't see the kind of structure.
Yeah, I think that's right. I think it's a crucial aspect of this. And let me just go back to a slide where we can see some of this. Right? And so this kind of development, I think, may actually be directly connected to your question. Because down here, actually the medium may be best approximated as a random walk, let's say through 5 screens or 10 screens, right? And there's a step at each one of those steps. And by the time we get up to the higher frequency, the scattering is much weaker because the bending angle of scattering due to a plasma goes as wavelength squared. So as we move down in wavelength, we've got much stronger bending angles here, much larger scattering. Up here, the scattering is much weaker. It's the high frequency observations that show the multiple arcs most clearly. So as we move upward. So in fact, you just helped me with that question, because I've been trying to put into words for quite a while what that progression really represents. And I think your question is actually focusing on the key thing, that at the low radio frequencies, the medium is looking more like a continuous medium with a set of scattering screens. At the high radio frequencies, we're just seeing single scatterings off of each of the individual screens. There you go. Okay, let's write a paper. We'll include Dylan. Yes?
So for this pulsar you described good. So dispersion measures are 1.6.
I think I made a mistake on one of my slides. I said 1.6, but then I saw on his slide, he said 2.6.
Well, it's
yeah.
similar kind of order magnitude.
Yeah.
We're talking about 1 to 2.
Yeah.
So, and you said there are about 20 scattering screens?
Yeah.
So if I divide 1.6 by 20, we're talking about something like 0.5, 0.6, 0.4 something. So it's really small. So what kind of density are you expecting to see these?
It's a very, very good question. It's a very good.
And you don't know the distance either. You don't know density, you don't know the distance. How can you exclude the possibility that this really comes from the solar system?
Yeah, okay, it's a good question. Very good question. So we do know the distance. We do know the distance to those screens. So if we go to that Reardon slide, and I didn't make this very clear, but if we go to that Reardon slide, let me go to, where are we? Okay, if we go to here. Let me make it a little clearer. This pulsar is in orbit around a white dwarf. And so, and it's a 5-day orbit or something like a 5-day orbit. So that kind of velocity, moving back and forth, that kind of modulation, they are able to track that, as well as the smaller velocity due to the Earth's motion. And so both of those transverse motions act to modify the curvature. So if we were to see a movie of this, you would see this network of 20 screens. You would see this opening up and closing, opening up and closing. They have solved for all of that, and using that information, they're able to get very precise screen locations, and those screen locations are well outside of the solar system. They are, it is very interesting to think about the solar system and to think about scattering in the solar wind and so on. But, and I don't have the numbers right at my fingertips, but the dispersion measure contribution of the solar wind is down at about, I think, about the 10 to the minus 3 parsecs per cubic centimeter level. So even small compared to the arithmetic that you just did. But I'm sorry, and I'll just restate, the key thing is they're able to locate the screens quite accurately, and they're all, most of them are just in the broad interstellar medium, except for a set of them that are associated with the bow shock itself.
I have another question about the pulsar and the white dwarf. It's a binary system.
Yeah.
How can they get together? White dwarfs come from the low to intermediate mass star, and pulsar comes from a massive star. Right.
So other people can help me on this, but let me, right, and so at least in the case of, well, and this is a millisecond pulsar, right? Yeah, so the standard scenario here is one where we start off with two main sequence stars, a more massive star, a less massive star. And that more massive star goes supernova, and it forms the neutron star, and there was not enough energy in the explosion, or the geometry wasn't right. The system remains bound. Okay, the system remains bound.
Yep. It's a pulsar. So do we know the age of the pulsar?
Yes, the age of the pulsar would typically, in this case, be like 1 billion years. Okay, there are two broad populations of pulsars. There are the young pulsars, which are the majority that we know of, which have characteristic ages of 10 to 100 million years. But then there is a group of millisecond pulsars, and the millisecond pulsars have this different formation scenario where...
Black widow kind of thing.
the Black Widow, right? The first one, the first supernova goes off. There you have a neutron star and a main sequence star. And then as the main sequence star evolves, right? So something like the sun, it evolves and it starts to overfill its Roche lobe, overflow, and then that material gets accreted down onto the neutron star. It spins up the neutron star, and so the neutron star had been dormant as a pulsar because the magnetic field had decayed, but now it's spinning much more rapidly, and now it can turn back on as a radio pulsar.
So the system is moving in this direction. This arrow says, right?
Well, the arrow,
And
I mean,
also
this
the
is on the
pulsar,
sky.
like if
It's on the sky.
Yeah, that's fine. And
Yeah.
the pulsar has a shape. It looks like the system is moving this direction. So that means that it has to come from the other direction. So from the other direction, do you see any clusters or anything?
You know,
That's
it's
pointing some clusters or
you know,
associations.
it's a gret question, and there are
It's been
some
years.
there are some cases out there in which people have been able to pretty convincingly trace back to the birthplace of a pulsar that has then been shot out. I mean, through the supernova explosion, right? The supernova explosion being asymmetric, and so the neutron star gets jetted out. And so there are some examples using these pulsar bow shocks to trace back to a birthplace. And then typically what people are looking for is they're looking for supernova remnants. And so they're finding a supernova remnant that was the birthplace of the neutron star. Great questions.
You said 1986, you said not too many people here. You said nobody here has been around. No, I got my PhD 1 year before you did.
Okay. There we go. Okay.
Is there any other question? I think we can continue our discussion outside because we are running out of the time. So if there is no more quick question, then okay, then let's thank them again.
Thank you.